Hello, and welcome to Virtual Investor Conferences. On behalf of OTC Markets, we are very pleased you've joined us for the Small Cap Growth Conference. Our next presentation of the day is from DarkPulse. Please note you may submit questions for the presenter in the box to the left of the slides. You can also view a company's availability for one-on-one meetings by clicking Book a Meeting in the top toolbar. At this point, I am very pleased to welcome Dennis O'Leary, Founder and Chief Executive Officer of DarkPulse, which trades on the OTCQB venture market under the symbol DPLS. Welcome, Dennis.
Hi, thank you. I appreciate that. So yeah, I'll get right into it. DarkPulse Technologies, again, traded on OTCQB and DPLS. We have a website, darkpulse.com, that does have a deeper dive, I guess I could say, on the solutions that we'll talk about today. This is going to be very high level. I'm going to try not to get too in the weeds on the technology, but you're very welcome to ask any question you like, and I'll try to answer those as much as I can. So I'm going to just start with the business overview of the company, and DarkPulse has a patented sensing technology. It's something called Brilliant Optical Time Domain Analysis, BOTDA, and we have several patents. And just a really brief history on the company. I spun the company out from the University of New Brunswick in Fredericton, Canada. Myself and the original PhD that invented the technology, Dr. Anthony Brown. So it's a patented sensing technology. It enables continuous real-time measurements of temperature and strain. We collect a whole series of data, but really just boils down to looking at two things: temperature and strain changes. The interesting thing, there's also a patented technology that we utilize that allows the data to flow at 60% the speed of light. There's just nothing out there in the market that comes close. And as we go through the technology, you'll see why the speed of the data is really important. So it allows users to identify issues earlier and visualize problems with minimal downtime and disruption to their operations. The technology is applicable to live, dynamic, I'll say, critical infrastructure and structural health monitoring, including bridges and roadways, buildings such as smart cities, pipeline monitoring, perimeter and national border security, and again, more importantly, structural health monitoring, which would include aircraft structural components, and then mine safety, another really interesting industry that we are involved in. So there's a well established number of sectors. Again, I'll say overreaching. The best way to describe it would be critical infrastructure, key resources, and we do have a global operations footprint that I can get into towards the end of the presentation. We do have a new presence in Dubai, which is really the gateway to the Middle East and North Africa. And again, we could go further into that as well. I have a timeline of the business evolution. We talked a little bit, again, founded in Canada, purchase of a series of patents that was bought from the University of New Brunswick. That was by debenture. And then we did in 2021, we went through a series of key acquisitions that really the idea was to bring more capabilities and that global footprint to the company. We had acquired a company in the UK named Optilon, and we carried through from 22 to 23, ended up with a force reduction and essentially purchased key assets of that company. And now I'd say really the most important piece of the acquisition was the technology engineering team based in India. And again, we can go into a little bit deeper on that. The company also launched in 2024 DarkPulse Aero, and the Aero division is based in northern Florida, and has the capability to manufacture custom drone platforms and various, navigation type software technologies that we have as well too. And then, as I just mentioned, 2025, we incorporated DarkPulse FZCO, That's in the free zone located at the Silicon Oasis in Dubai. So again, I guess just hitting some highlights. So where we are today, new hardware design. This has been really an evolution of the hardware. When we first purchased the patents, there was a desktop model, I'll call it a benchtop model, probably just under the size of a Volkswagen automobile. And the cost was north of $200,000. This is, 2010, 2009, 2010-ish. And then, just technology in itself and hardware improves over the years, but then also our desire to reduce the cost of production, of manufacturing, and then, of course, increase the capabilities and then reduce the footprint. We've actually got the system where it's rack mountable. So it slide into the rack, and there's different iterations, or I guess flavors of the technology that includes some of the external hardware that these types of systems require that actually brought in internally into the chassis itself. We also launched the world's first intelligent bridge. That was in Marysville, California, and it's called the Huncut Bridge. What we did there is, typically when you're building a major pour, a concrete pour, and you're building, what eventually becomes a bridge, they generally use things called thermal couplings. And what that does is it allows them to understand, that the concrete that they poured has cured properly. It did not show them the curing process. It did not show them voids in that pour. And once the concrete is hardened, that device, I'll just call it a sensor, but a thermocouple it's called, is completely useless. They can't use it for any other monitoring. What we did is we ran our system, which I'll get into. Essentially, it's a piece of hardware box, and then a run of telecoms communication cable, standard single mode fiber cable. And what we did is, aside from showing the curing process, we were able to alert to voids before they were a problem. We obviously told them that the concrete cured properly. And then more importantly, after the construction ended, the system has the capabilities to where we can detect through temperature sensing water seepage through that pier. So there's some piers that are in the Huncut River, and there's others that are not. The ones in the river, again, we can show seepage. More importantly, we can detect internal structural anomalies, things that will could lead to a bridge collapse long before there's any kind of structural problem. So that's, I think, a good way to show the differentiator of the technology between what's currently used and what could be used. And then I think more interesting is this now AI-assisted virtual reality user interface. And the VR interface is actually programmed, for Oculus, but then now also, the Apple headset. So by doing it on two different platforms, the system can use a VR headset from really any system, any commercially available or non-commercial available VR headset. Our user interface is available by using that device, and we can go into that a little bit as well. That I think I think it's pretty interesting when you compare to what's actually out there today in terms of user interface. And then I did mention a little bit how we're headquartered in New York, and then also Dubai. We're again located in the free zone, and Dubai is the gateway to Middle East and North Africa, and as well as a consolidated market, for major oil and gas companies and technology companies. The company has 7, I guess, work visas, the best way to describe it, and we plan to start hiring and filling out the team based in Dubai in the first quarter of next year. Again, I guess just more of an overview of a little bit of high points. Again, best in class protection in real time. Again, the resolution we'll get into is what really allows us to say best in class protection. We also, with using the sensing systems that we do, and again, I'll get into the actual physical, what is the system? There's a lot of push into AI-based, cameras that monitor structural health. With using the fiber sensing system, it's both above and below ground solution. So if you have a buried pipeline, an AI camera is really not going to help you much. Maybe detect, a leak, but at that point, it's, the horse is out of the barn, so to speak. It's a complete end-to-end solution. And again, this goes back to the resolution where we have 20 millimeter resolution. We've had 10 millimeter resolution in the lab. So roughly 2 centimeter resolutions, which means, we're not going to miss anything. And systems now, just for instance, give an example with pipeline, at best, because of their resolutions being pretty terrible, they can monitor, very large size pipelines. They cannot go full end to end, which would be, from let's say midstream perspective, like a large 36-inch or larger diameter pipeline all the way into, let's say, a refinery. They're not able to do that last mile. Whereas because of our sensitivity, we actually can detect pipes down to, actually a diameter of 2 inches. So, we could go midstream, but then also, again, right into the refinery. And then fully integrated user interface. We essentially can plug into any interface. And that's important, especially in different industries like power and things of that nature, where you want a dashboard. And you need to be able to, be inside the current dashboard, not have, a separate window operating your software where, it becomes cumbersome. And then I wanted to just show you, I guess, in terms of the companies, how we would go after a project. So initially we start with DarkPulse Aero. That's, an aerial survey, could include an environmental survey, an environmental impact type of survey. And then once we collect the initial data, that goes over to Optilon. Optilon engineers then design the installation portion, speccing out the tech, what kind of software, what sort of groundworks needs to be done in terms of installing into a ground or onto a pipeline. And then DarkPulse, actually, does the installation. We commission the software and the hardware, all remote. And most of the hardware now is actually self-commissioning. We used to have to have an engineer do it manually, but now the software actually commissions it. But we can dial into that piece of hardware from anywhere in the world. And then also, the maintenance of the system is done remotely. And then more importantly, the monitoring, as well. And then again, that's sort of the last part. I think the most important part, because in terms of revenue models, we're essentially like a Cisco Systems where, the goal is to, reduce the cost, the actual hardware cost, to a point where, most of the revenue you're coming from hardware sales. Basically, your revenue is very mountainous, I'll say, mountain and valley, right? Whereas with licensing and software sales, it's a steady ramp up as you add more end users. These are monthly fees that are paid to the company. So yes, we have the hardware revenue stream, but more importantly, we have the monitoring and maintenance revenue stream as well, which is much more steady and offers 100% return on investment for that. And I'll just go very briefly again. So DarkPulse, the monitoring and the maintenance. DarkPulse, we have a real-time 24/7 monitoring, by use of a custom built interface, this virtual reality, user interface, which, you don't have to, you're not limited to just, a VR headset. It can be applied and used on a desktop or, things of that nature, or a laptop, really any device, anywhere in the world. And again, with this new, I'll say data handling, intellectual property that we're working with, the speed is 60% of the speed of light. It's the fastest thing that's out there. And, critical, I think, especially when you're in more remote areas, to be able to move data around quickly, especially over satellites. Satellites, historically slow, regardless of, let's say the size of the pipe, but, it's not there yet. But with using our technology and with this data handling tech now too, we could still say real time in terms of, the monitoring and the display of the user interface. And then the technology, I'm going to go not deep at all. We can go deeper in questions. The way I describe the BOTDA system is it's a fiber radar. And essentially what it is, you have a piece of hardware. You can see that there's, this orange line that is a fiber optic cable. Again, a single mode fiber optic cable. And, you can run these things hundreds of kilometers. There's different recommendations in terms of when we would put a box along that fiber. Generally, to retain like that ultra high resolution, let's say 10 to 20 millimeters, you're looking at, basically, 10 to 15 kilometers, you'd put a piece of hardware. But essentially what's going on, the box is sending a laser light down the cable, the sensing cable. And then it's really it's like a, time, speed, and distance calculation. Just very much like a radar, a pulse goes out, except again, it's a light pulse inside the fiber. And then we know through timing where that pulse is along the fiber. And that sends a signal back to the hardware. The software then, I guess, translates that into, stress, strain, temperature at a specific location. And I think really more interesting, and I'll show you some screenshots of the UI. The data is overlaid onto whatever we're in. So if we're on a pipeline, the data sets are overlaid onto the pipeline. One of the examples I'll show you is the data overlaid onto a bridge. And so you're seeing the bridge with 3D in real time color coded in terms of stress, strain, temperature. But again, just the simplest form, it's exactly like a radar. Because again, the pulse goes out. We know how far down the sensing cable it is, and then the software converts it into what we're looking for. And again, just a brief overview. BOTDA, about 100 years ago, Leon Brion, French scientist, discovers how light scatters in different medium. Glass in this instance, in a fiber optic cable, and essentially we're measuring the shift in this beryllium, band, I'll call it, without getting too technical. And that shift actually gives us the measurement of strain and temperature along that fiber, like I was just talking about. And it's unlike the traditional acoustic sensors in that it provides extremely high resolution, ultra high resolution, and like I say, real-time data over long distances. And then go a little bit deeper in how it works. And you guys will have the slides, so again, I guess that would be helpful too. So I mentioned a little bit the laser pulse is sent to the fiber. The reality is, because of our dark pulsing technology or a technique that's patented, we pre-light that fiber. So we excite the glass. It's preheated, we'll say, and then we turn the laser off with just a picosecond. And essentially a dark pulse travels down that sensing cable, and that's what gives us the ultra high resolutions. The signal to noise ratio is no longer a factor. And more importantly, we can detect temperature and stress and strain on the same fiber simultaneous versus other types of BOTDA or acoustic sensing. There is a cross sensitivity between stress and strain, I'll say, and temperature. So you cannot take those measurements at the same time with any other system that's out there. Ours we can, because of this dark pulsing technique that's been fully patented. I'm trying to see, I guess I'll go to the next slide. I don't want to get too deep, but I'm going to go over just briefly acoustic sensing. So acoustic, kind of just like it sounds, detects vibrations and sound along the sensing cable. Usually use a Rayleigh scattering or backscattering, it's called. So very similar type of technique, but they're looking again for vibrations and sound. And it basically is interpreting the acoustic energy from digging, drilling, hammering, walking. You've seen things like this. Really different types of movement that are near the fiber. The limitations of this is the resolution is extremely low, 10 to 15 meters. So anything smaller than 10 to 15 meters, that system is not going to detect it whatsoever. Again, we're talking like, a centimeter. Anything that moves, down to a size of a centimeter, and let's say in a perimeter, we're going to know it's there. Acoustic, you're probably not going to know it's there. It's going to take a considerable movement, I guess. Really, I guess an acoustic wave, a maximum amount of energy to actually say, oh, okay, somebody's crossing, a border or a perimeter kind of thing. They have high false alarm rates as well. Wind, vehicles, animals, all kinds of things that create vibration that interferes, and it's very hard to differentiate hey, is this a person approaching my pipeline to do bad things? Is this a person trying to tunnel under the border? Or is this a person trying to, break through a perimeter? So again, very high false alarm rates. It's also unable to detect tunneling or really subtle underground activity. They can't see tunneling at all. And then they're very typically reactive, only sort of detecting these sort of major, vibration types of events. And then sort of the inner workings, distributed acoustic sensing, it interprets, again, this vibration signals, caused by these diggings or vehicles or wildlife, things like that. And then their system, the software will determine or distinguishes between, is it a vehicle, is it a person? Again, because of the low resolutions with this type of technology, it takes quite a bit of work to do, the signal classification. But misclassification really remains very common, especially in noisy environments. And I'll show you an example. Like again, for the U.S. border, most of the U.S. border fence is along, a publicly accessible road, and vehicle traffic driving by drowns out any acoustic signal of somebody tampering with the wall or trying to climb the wall of the fence. So conditions like wind, rain, even sedimentary shifts in the soil can trigger alarms, which reduces the reliability in field deployments, where, especially along a border where, accuracy, really is vital. So I'll kind of drill down into perimeters and borders. Again, we just talked about, so it makes sense too. So this is an interesting slide. So again, upper left, this is the deployment of an acoustic sensor system. The screen on the computer on the left is difficult to see, but I do have it down below here. And this is called a waterfall screen. It absolutely just sort of drips in front of the user. The other thing, or really the downside, is that the person who's your security guy or your engineer has to sit in front of the screen and watch it in real time. Some systems now do have an alert box, but the reality is this is the image that you actually see on the left. And if it wasn't for those little hints, saying work is walking down a road, a truck drives up, a truck leaves. I'm a tech guy. I would have no idea what that is actually telling me. And then you look to the right side of the screen. And again, we're talking major differences in resolution, which I'll get back to. But this is a screenshot, a grab of our VR interface. That's the Huncut Bridge. And that clear bubble, that was an idea that the team and I came up with, where this bubble, you can bring it up, and we could do live demos if people are interested at some point. You can contact us. But you can make this crystal ball appear through the headset, and then move it around with your hands and push it into different things. This one is pushed into the Huncut Bridge, and you can see into the bridge itself. And the display of the data is in real time in color. So, and these colors, by the way, the red and the orange, that's based on mu strain. How much strain is going on there? It could be also based on temperature, and the end user can decide what those colors are. So it's totally up to the end user. And again, acoustic sensors at best 10 to 15 meter resolution, very poor resolution, and miss incursions more than 70% of the time. And that's if there's nothing funny going on, no funny business, which we'll get into what actually occurs at the border. And then again, on the right, upper right, is a picture of our unit. And again, zero false alarms. It misses zero incursions. And again, this instance, we're calling it, 20 millimeter resolution. But again, in the lab, we've got it to 10 millimeter. And there's different ways if somebody needs that type of, of resolutions, which I don't think there's a deployment that I would know of. Maybe an aerospace deployment, but that's easily, we can attain 10 millimeters in an aerospace environment. And then again, just getting a little bit closer with the user interface, the one on the left, again, it actually drips down. It moves down from top to bottom. And these little dots and lines start come up as the end user is actually sitting there staring at the screen. Whereas again, on the right, this is Hunt Cut Bridge. This is a skeletonized view that's available too. You could change the view of the structure. If you don't want to see, kind of like a game looking structure, you can go into skeletonized. And again, on the right, this is show you stress and strain in color in 3D in real time. And with the VR headset, I could fly to that location on the right, that like again, let's say the flat part of the bridge. I can stand in that bridge and stick my head down, bend down, and my head goes into the bridge structure itself. I could look around and I'll see the different colors, along the roadbed. That tells me the stress and strain. Okay, and then I think more importantly, more towards the left side of this image, it says direction and intensity. And you can see the 3D color now, it's kind of raises up off. It's like an arch off of the roadbed. That's another game changer in terms of fiber optic sensing. The system itself can see the position of the fiber. So in this instance, the stress on the bridge is coming up out of the bridge, not down below, right? This is going up out of the bridge. And then more importantly, the length of this color coming up off the roadway is the intensity in mu strain. So not only now am I seeing like the right portion of the bridge, I'm seeing stress and strain in color, I'm actually seeing the direction of the strain, the stress, and the intensity in mu strain, which is, engineers like to see these things. And again, if I were to stand on this bridge with my VR headset, when I look, at this portion that, again, I'm highlighting with the direction and intensity, I see that color come up off of the roadbed, or I see it go below the roadbed. And again, I can see how much strain and what direction that strain is in. So that's, there is no system out there that can actually do this. And actually it's extremely important for a lot of different reasons. So we'll continue down. I brought up a little bit about border security, and I have some great stats here. So this is by state along the border, total miles of border. So we'll grab Texas right off the top, 1,254 miles of wall along the Texas border, and 1,100 miles have access to it by public roads. So the image in the background that's a shot in Texas. The roadways next to the border fence. Okay. So this noise from these vehicles, you're not seeing anything. If anyone's climbing that fence, it's completely invisible to